Good evening, everybody. I am Vibhu Swami from PowerTech Consultant. Today we'll start our webinar number 28. Let me share my screen with you. So, in the webinar number 28, we'll discuss about chapter 1, book 1 of chapter 5 of book 1, that is material and energy balance. And this is in book 1, that is general aspects of energy management and energy audit. Material balance is particularly material and energy balance are very important as far as uh, energy audit is concerned. Why? Because material needs to be conserved as well as energy needs to be conserved. Material balance is basically it is based on law of conservation of mass. What law of conservation of mass states that matter cannot be created or nor destroyed. So matter is neither created nor destroyed. That is law of conservation of mass. Material balance is based on law of conservation of mass. Material balance is a mean to maximize product yield and minimize cost. What is the advantage? Why you need to do material balancing? So that the product yield is better and wastage is minimum and the cost is also minimum. Now, material balance are very fundamental to the control of processing, particularly in the control of yield of the products. Material balance can be determined from the conceptual stage to final production stage. Initially, material balance are determined in the exploratory stages of new processes, improved during pilot plant experiments, when the process is being planned and tested, checked down when the plant is commissioned, and then refined and maintained as a control instrument as production continues. What does it means? It means material balance you cannot analyze at one go. During designing stage, you come up with a material balance. Yes, this will be input material, this will be output material, this much of loss will be there, this much of material will be evaporated, and this will be my product yield. Then when it is, then you run a pilot project and see how the material balance is behaving. And it is again fine-tuned. Then after that, when the product is or the plant is commissioned, again the material balance keeps on changing. And further by controlling, by giving additional input, and by designing the process, by improving the process, the final material balance is obtained. And this helps in increasing the yield of the product and thereby minimizing the cost of the product. In view of the same, material balance is very important. Similarly, energy balance. And what energy balance tells? Basically, it is based on law of conservation of energy. What it states that energy is neither created nor destroyed, simply converted from one form to another. Energy balance, why you required to do? Because it is a means to reduce energy consumptions and thereby energy cost. So material balance is basically to reduce the product cost or maximize the yield. Energy conservations or energy balance is related to reduce energy consumptions and energy cost. Both are very important for an energy auditor point of view. Now let me ask one question. If energy cannot be created, energy cannot be destroyed, it only converted from one form to another, then what is the need of conservation of energy? Energy is same, it is not being created, it is not being destroyed. Whether is there any need for energy conservation in that case? Yes. Answer is energy conservation is very important in our life. Why? We are conserving the useful energy. So all available energy are not useful for us. They are available, but they are not being utilized. So what we are doing, but by conserving energy, in fact, we are conserving the useful energy. Now, what is the purpose of material energy balance? To assess the input, conversion efficiency, output, and losses. For any process, we need to understand the input, output, and losses to quantify all material, energy, and waste streams in the process or a system. Simple, what is the input material, what is the output material, what are the losses, can only be found out by material balance. It is a very powerful tool for establishing basis for improvement and potential savings. What you are doing, you are saving both material and as well as energy by conducting material and energy balance. Therefore, these are very important tools as far as improvement and potential savings are concerned. Now, what are the major component of material and energy balance? One is, now let us examine this is a process or unit or operations. Now these are raw materials, chemicals, water, energy or power. Some amount of products are being recycled, and this is reusable waste in other operations. Now what is the output? Output is basically sometimes gases are found, so gaseous emissions is one of the output. Product, of course, byproducts, waste water, liquid waste, solid waste. So these are the waste. These are the gaseous waste. So these are the major component of material and energy balance of a process or a unit or for any operations. Now, what is the basic principles? Basic principle says that the mass and energy going into the box must balance with the mass and energy coming out. That means in case of any unit, in case of any process, the total mass and energy going into is equal to the total mass coming out and energy coming out. So energy in should be equal to energy out, and masses in should be equal to masses out. This is known as material and energy balance. This is the basic principle. In this case, this is the unit operations. There is some stored material inside and some stored energy is also inside. So raw material is equal to stored material plus product output plus waste products, that is material balance. Similarly, energy, some stored energy, energy in product, energy in waste, energy losses to surroundings. Now, this whole is basically known as mass and energy balance. What happens exactly? Sometimes this mass is not equivalent to this mass. What? Why? Because some kind of mass is converted to energy and goes out as energy loss. Similarly, some amount of energy is also get converted to increasing the yield of the mass. So when we discuss, we need to also discuss mass and energy put together. Now, the law of conservation of mass leads to mass or a material balance. What we studied? Mass in is equal to mass out plus mass stored. So raw materials is basically products plus waste plus stored materials. Now, in case this M is stands for mass or materials, R raw, P product, W waste, S stored. So total raw material MR is equal to raw material can be plenty. So raw material 1, raw material 2, raw material 3. This is total raw materials. Similarly, there will be many products. Product 1, product 2, product 3. These are total products. Waste, there will be number of wastes. So W1, W2, W3 total waste products. Similarly, stored products are S1, S2, and S3. So what is the principle? Total raw material is equal to total product plus total waste plus total stored materials. Now, if there is no chemical changes occurring in the plant, the law of conservation of mass will apply to each component. So that for component A, that means mass of A entering in materials, mass in entering materials is equal to mass in the process exit material plus mass stored in the plant. This is applicable when there is no chemical changes occurring in the plant. Now let us examine an case of sugar plant. What happens exactly in a sugar plant? Total sugar goes into this plant, but is not equal to the total purified sugar or the sugar in the waste liquors. Why? Because some sugar is either burned or chemically changed, or it is going unnoticed down the drain somewhere. That means there may be some losses, there may be some chemical changes, some sugar might be burnt. In this case, what happened exactly? The mass entering materials is equal to product plus waste plus stored plus this is known as the losses, or basically unknown losses. MAU, that is the A basically is a component. So mass of unknown losses needs to be identified. So the material balance what it says, raw materials is equal to product plus waste product plus stored product plus losses, where losses are unidentified material. So this is the clear philosophy of material balance. Mass in is equal to mass out plus mass stored, and of course with some amount of unidentified material. Similarly, let us come to energy balance. Energy in is equal to energy out plus energy stored. Now, in this case, R stands for energy entering to the systems, raw materials particularly. This is P, energy leaving with the products. This is total energy leaving with waste materials, W. This is the total energy lost to surrounding, S. And sorry, EL is equal to EL1 plus EL2 plus EL3. This is the total energy lost to the surroundings, EL. And ES is the total energy stored. ES is equal to total energy stored. So this is basically energy balance. Energy balance are often complicated because forms of energy can be interconverted. For example, mechanical energy to heat energy, but overall the quantities must balance. That means energy balancing is relatively difficult because it keeps on changing from one form to another. So for which it is very difficult to conduct energy balance. But both mass and energy balance are important for energy auditor. Now let us examine what are the process, classification of process. Now as I told you, the previous unit operations, this is one unit operation in which we provide raw materials, energy, and apply control systems. Some energy is wasted, and you get product, waste product, and subsequent unit operations, and you get byproduct and some waste energy also. Now, one is when you classify a process, it is basically various types. One is steady state process, unsteady state process, continuous process, batch process. So we'll have to know what are these processes to understand the mass balance and energy balance put together. Now, steady state process is the process where none of the process variable changes with time. That means all the process variable remain constant. It does not change with time. Unsteady state process is one where the process variable changes with time. In this case, process variable keeps on changing with time. Now, how the process was built to operate? Another line of classification. One is continuous process. Is basically it is the that means you are feeding a stream or product input, product and stream of energy are going inside the process and coming out. It is a continuous process. Oil refinery, distillation process are basically continuous process. But what is a batch process? Batch process is basically where feed streams energy are fed into the process to get it started. The feed material is then processed to various process steps. Finished products are taken out specific times. That means initially you charge the feed into a vessel, process is started, no mass is added or removed from the vessel during the time process is going on. Process parameters are usually monitored and controlled. After certain conditions or after certain peak time, the products are removed. So this is known as batch process. It is a discontinuous process. But continuous process is basically a if the process is continue to operate, oil refinery distillations. What is the example of batch process? Like furnace. You charge material, apply heat, apply electrical energy, and remove those materials after certain time. So that is basically a batch process. Heating is also a batch process. Furnace heating is also a batch process. So these are the classification of process. Now come to material balance. Level of material balance. Basically, there are three types of level. One is overall material balance. Normally, it is done for a complete plant. Now, section-wise material balance, you can have one section, one department, let us say SMA, steel melting shop, or rolling mill, or blast furnace. These are each sections. So, or department or different cost center. So, you can carry out also material balance for section-wise, and it helps particularly to prioritize the focus area for efficiency improvement. So section-wise material balance helps to prioritize the focus area for efficiency improvement. Equipment-wise material balance. That means you are conducting material balance at equipment level. It helps in performance assessment of the equipment. These are basically needed for equipment. So there are three level of material balance or how it is conducted: overall, section-wise, equipment-wise. Then material balance procedures. There are three procedures again. One is for define the basis and units, which is very important. Draw a flow chart. Yes. And after that, write the material balance equations. Now we'll little bit understand what are these procedures. Define basis or unit. That means basis of calculation is chosen. That is mass for batch process, flow rate for continuous process. Why? These are important. Batch, it is a discontinuous process. Therefore, what the mass is going into the system is calculated. But in case of continuous process, the flow rate, that means mass flow rate with respect to time, is found out first. Now, the unit can be expressed in various ways. These are very important. One unit or one wage is weight versus weight. That means W by W, which tells that weight of a solute divided by weight of a solutions. That means the weight of solute with respect to the weight of solution. That is known as WW. Weight volume, weight by V. Weight of the solute with respect to volume of the solution. Molar concentration, M. M means the number of molecular weight of the solutes expressed in kg in 1 cubic meter of solution. That means if a salted or salty water is there, salted water is there, some salt has been added, then you calculate the molecular weight of the solute in kg, divide it with 1 cubic meter of solutions and find the molar concentration. Then mole fraction, number of moles of the solute divided by total number of moles of all species present in the solutions. So it is basically solute moles divided by total moles of each constituent present in the solutions. So these are the four ways how you can express the mass, and these are the units. So W by W, W by V, that is weight per volume, molar concentrations, M, mole fractions. We'll study in details while solving numericals on these. Next is draw a flow chart. Draw a flow chart means, let us say this is a reactor, this is a separation and purification line, this is the final product. Then this cycle of on-reacted material, it comes from the separation and purification unit, goes to the reactor again. You get some waste and byproduct or co-product. So this is basically a process flow chart. You have to draw lines, you have to draw blocks, how the material is going in, what are the negative or feedback material is coming out of the process, again is recharged. Sometimes scraps in case of steel melting shop comes out and again recharged. Some waste material also comes out and again re-entered into the process, and you get a final product. So boundary is established so as to identify the flow streams in and out. So you have to understand what are the in and what are the out material. Process flow is constructed stepwise. You need to construct the process flow diagram in a steply manner, a stepwise manner. Now, what are the input? Input are basically, it could be raw material, it could be water, it could be steam, energy, electricity, anything. Process steps should be subsequently drawn from raw material to finished product. So from raw material to finished product, the process steps should be sequentially drawn. Also, you have to note down the intermediate and other byproduct. The operating process parameters such as temperature, pressure, percentage of concentration, etc., should be represented in the process flow chart. Now, the flow rate of various streams should be also be represented in the appropriate unit like meter per hour, kg per hour. In case of batch process, the total cycle time should be included. Waste byproduct could include solid, water, chemical, energy, anything. For each process steps, unit operation as well as for entire plant, energy mass balance diagram should be drawn. Output of the process is the final product produced in the plant. And after that, write a material balance equation. So these are the steps for material balance. So here exactly what you do, while drawing the process flow chart, you have to showcase all the input, output, co-product, byproduct. Then you have to write all the unit, mass unit. If it is a batch process, you have to write the total cycle time. Then you have to maintain or mention the temperature, pressure, concentration, everything. And after that, you have to calculate, analyze, and write a mass balance equation. So this is all about material balance. Now let us do some numericals. Numericals are very important in this chapter, and that's why we'll solve some numericals now. Now in this example, the problem is that a solution which contains 10% solid mixed with 25% solid solution, and single output is, which is 20% solid, is removed. If the 10% solution enters at 5 kg per second, what are the other rates? Assume no accumulation. So this is important. Assume no accumulation. That means all masses are entering is going out. Now first what we have to do? We have to find out the basis. Now solution A. What is the input? 5 kg per second. Now solution B, input we are not knowing, we need to find out. So we call it x kg per second. So these are two input, solution A and solution B. So the process flow diagram says that two solutions are going, both are input, and then you are getting an output, that is y kg per second. So assuming it is a continuous process, what you can write? Total input is equal to total output. Now, what are the input? A and B are input. What is the output? C is output. So A plus B is equal to C. So this is the basic material balance. That means 5 kg plus x kg is equal to y. Because why? There is no accumulation is happening in the process. Now let us come to solution A. Solution A contains 10% solids. It is mentioned here. Now solution B contains 25% solids. So there are here two solutions. One is 10 with 10% solid, another one is 25% solid. So now solution C contains 20% solids. So how to write the equation now? Now let us write the solution, or let us write the equation for solid. So all solids should same. Solid entering into the system is equal to solid outgoing to the from the system or coming out from the system. So, if I balance the solid or do material balancing as far as solid is concerned, what I can write? 0.5 sorry 0.1 10% into 5 kg per second is equal to 0.25 into x is equal to 0.1 into 5 plus 0.25 into x is equal to 0.2 of y. This is the solid or equations or material balance equations for solid. Now similarly, I can also calculate the balance equation for liquid. So what is liquid? In the first input, it is 10% is solid, so 90% is liquid. So 0.9 into 5 plus, in this case 25% is solid, so liquid is 0.75 into x is equal to 20% is solid, so 0.8 into y. So these are the two equations. Now, and there are how many variables are there? X and y, two variables. So it is very easy to solve these two equations. By solving, I got x is equal to 10 kg per second, and by putting x anywhere of the equation, I got y is equal to 10-15 kg per second. So if solution 10% solution, if the solution A enters at 5 kg per second, the other rates will be, that means solution B input rate will be 10 kg per second, and output C yield rate will be 15 kg per second. It is very simple. What exactly we have done here, though problem is very complex, but we have streamlined it by doing two mass balance. That means for solid, we did a mass balance. For liquid, we did a mass balance. Also, we also consider that total product entering is equal to total product coming out of the systems. Now come to another problem, 5.2. A solution which is 80% oil, 15% usable byproducts, 5% impurities enter into a refinery. One output. So solution is one. One output is 92% oil, 6% usable byproducts. There is another second output, which is 60% oil, and the flow rate of the second output is 1000 liter per hour. Here also, there is no accumulations percentage by volume. This is weight by volume. Now, what is the flow rate of the output? That means we need to find out what is the input flow rate. Then what is the percentage composition of 1000 liter per hour output? This output is coming out. So what is the percentage of compositions of this output? And what is the percentage of original impurities are in the 1000 liter per hour output? So we have to also find out what is the original impurities, what is the percentage of original impurities are there in the 100% liter per hour output. This is no doubt, if you look into the questions, it looks very complex, but can be easily solved by material balance. Now here, what is the basis? How many inputs? One input. And it is not given, so let us assume x liter per hour. This is the flow rate. Then output, there is another output, B. Let us assume it is y liter per hour. This is the flow rate. Now C output is given, 1000 liter per hour. So there are A is equal to B plus C. That means X is equal to Y plus 1000. If I write the material balance equation first. Now let us write individual material balance for oil. So all the oil going in is equal to oil coming out. So 0.8. Why 0.8? 80% is oil. 0.8 into X is equal to 92% oil in the B. That means 0.92 into Y. 6% is in C. That means 0.6 into 1000. So this is equation 2. Similarly, usable byproduct will be 15%, 0.15 into X is equal to 0.06 of Y. Now, V into 1000. Now, since I don't know the percentage compositions of 1000 liter per output, I consider that another variable V or unknown variable V. So, V into 1000. Similarly, impurities is 5%, 0.05 into X into 0.02 into Y. Why? Because 92% oil, 6% usable byproduct. So it put together it becomes 98. So 2% is basically impurities. So 0.02 and W I don't know. This W is basically the impurities in the later output stream C. So here I assumed two variable V and W. So this is my fourth equations. Now, if 60% oil is there, now what is the input? Input contains oil, byproduct and impurities. So what are the rest? 40%. Rest 40% will be byproducts plus impurities. As far as product C is concerned or output stream C is concerned. So output impurities and UMBP, that means V plus W will be 0.4. So these are the five equations. How many variables? X, Y, V, W. So it can be easily solved. Now these are all mathematics. You solve first for X and Y. There are two equations. Basically, sorry, these two equations are there. So with this, I can solve the X plus Y from equation 1 and equation 2. From there, I got Y is 166 liter per hour. That means the output product rate, and the input product rate is 1000 liter plus 1666. So 266 liter per hour is the input flow rate. That is the first question. Now, if I substitute this X and Y value, I'll get E as 30%, W as 10%. So the composition of 1000 liter per hour stream is 60% oil and 30% usable byproduct and 10% impurities. This is the third question. The percentage composition of the, sorry, second question, percentage composition of 1000 liter per hour output. Then the impurities in the input stream is how much? It is 0.05. Input rate is 2666. So what is the impurity? 133 liter per hour. Now impurity 1000 liter per hour stream is 10%. That means it is around 1000 liter per hour because impurity is 10%. So impurities flow rate is 100 liter per hour. Therefore, percentage of impurities in 1000 liter per hour stream as percentage of input stream will be 100 divided by 133.3. It becomes 75%. So this is the percentage of impurities in the 1000 liter per hour stream as percentage input stream. So this is though it looks like a very complex equations, but it can be solved by using material balance, where you can find out the different type of yield, different type of product, different type of waste, different type of impurities for any type of process. Now come to the third example, constituent balance. Now skim milk is basically where fat is not there, and whole milk is basically the where the fat is there. Fat is removed from whole milk to produce skim milk. So skim milk is prepared by removal of some of the fat from whole milk. the skim milk is found to be 90.5% water, 3.5% protein, 5.1% carbohydrate, 0.1% fat, 0.8% mass. So this is my skim milk, and the constituent or the components are given. Now, original milk contain 4.5% fat. This is the original whole milk which contains 4.5% of fat. We have to calculate only fat is suppose is removed, then what are the percentage of fat is removed to produce the skim milk, and the assumption is no loss in the processing. Now this is 4.5% fat, and what is the fat in the skim milk? 0.1% fat. If you see this picture, roughly anybody can say 4.4% of fat has to be removed. No, this is not correct. Why? Because this is on percentage basis. So when fat is removed, this percentage of water, protein, carbohydrate also get changed. So we need to do certain material balancing to find out what is the fat is removed. Now let us, what is the basis? We have to assume certain units, certain basis. So let us assume 100 kg of skim milk, because these percentages are given. So we have assumed 100 kg of milk for a simple city. Now let us assume X kg of fat is removed. Now, therefore, for 0.1 kg of fat, let the fat which was removed from the to make skim milk is X kg. Now, what is the original fat? Original fat is, this is 0.1 kg because it is 0.1%. So 0.1% into 100 kg, it becomes 0.1 kg. So what is the original fat? And X kg is removed. So original fat is X plus 0.1 kg. Now what is the original mass in that case? Original fat is, this is 100. This is X kg is removed. So original mass is 100 kg plus X kg. And what is the original fat? Original fat is X plus 0.1 kg. These two equations are very important. You need to formulate these two equations by reading all these questions. And we don't require all these data, but this concept is required to find out to formulate these two equations based on the material balance. Now, what is given? The fat percentage is 4.5%. That means total original fat divided by total original mass is equal to 4.5%. So X plus 0.1 divided by 100 plus X is equal to 0.00045. That is 4.5%. Now this is a simple variable and single variable and single equation. It can be easily solved by applying algebra. So X is equal becomes 4.6 kg. Now, so the composition of whole milk is then 4.5 fat is 4.5 water, 4.5%. This is the, how you can know? Because what is the input material? This is X kg, X is 4.6, we found out. This is becomes 100 kg. Now 100 kg, 4.6 kg. So input material balance is 104.6 kg. Therefore, what is the water percentage in the original milk? The next question is given. We need to find out the compositions of the whole original milk. Now, what is the this water, protein, carbohydrate, fat, or sorry, water, protein, carbohydrate, as are not touched. They remain, the quantity remain same. So the percentage of this constituent in the original milk becomes, water will be 90.5 divided by 104.6 kg. It is 86.5%. Protein is 3.5 divided by 104.6. Carbohydrate will be 5.1 divided by 104.6. Mass will be 0.8%. So this is how we can calculate basically. And if you can divide it, also it will come in the same range. It will be 0.08 divided by 104.6, and it will come the same values for us. So this is how we can find out the constituent by applying mass balance put together. So with this, I stop the mass balance here. In the next class, we'll solve some more numericals. And here you can get some questions: what is mass balance, what is energy balance, what are the difference between them, and particularly you can be asked what is the procedure for conducting mass balance, and also we will be asked some numericals related to mass balance. With this, I conclude. Good night.